Hey, how you doing? This is Brian Fields, amateur radio call sign W9CR, and I have kind of a simple, basic thing that came up here. This came out of a discussion that people were having online about can you put, if you have a high current application, you only have cat5, can you put two conductors and just tie them together and get a little more current out of it? And there's some answers on this. Depending, yes or no. There's some reasons that you can't do it with, say, a normal branch circuit in a house and things like that. Ultimately, we're just going to look at this from a very simple DC perspective because, I saw one of the people, they said, well, they took their multimeter, they measured some wire, and hey, if you put one together, it's 0.4 ohms, and if you put two of them together, it's still 0.4 ohms. Well, that kind of gets into the difference there of how you're measuring, and with such a small piece of wire, you don't have enough resolution in most ohm meters to do it. So I have a couple test resistors here. These are nice precision, if you can see, 10 ohm, 0.01 precision resistors. I've even cleaned up with some abrasive cloth, cleaned up the connections on them because we're going to do some measurements here. What you really need to do this with is, and if you look up here, this is, I know it's not an Agilent, it's a Siglent, but it's a 2-wire, and you'll see it's actually in what's called 4-wire resistance. This is actually where you're using 4 leads to measure the resistance or something. I won't get into the details on this. There's tons of information out there. But like if you're using a very like a conductance meter or something like that, it's the same setup. It's basically an amp meter and a voltmeter together measuring and looking for a delta between them. Very simple, and you can tell me I'm wrong about how I said that, but it's kind of right. Again, I'm not going to get into the details of this because when you start getting into measuring very small amounts of resistance, you start having to take into account the resistance of these wires, the resistance of these wires, capacitive coupling, noise, thermal stuff. And I'll even show you some of the thermal stuff here in the demonstration. So from a general standpoint, let me show you what we have here. And they make a special, which I do have some, I just can't find them, a special probe for doing 2-wire. It would have 2 wires coming out of here, a current and a sense line, and they would go to alternate sides of this so that when you clamp it on, it would pick up the same. However, in this case, I don't have that. I have it, I can't find it. So take one of the resistors, put it in here on the current side, and now this will not give me a reading. But as soon as I put on these, and you'll see I'm going to put them in parallel here because they're essentially 2 separate meters. Tangled wires, the bane of the electronic experimenter. And I clamp this on here, make certain I got a good connection. And this is just one resistor, real simple. And if you go up here, we see it's 10.015 ohms, and these are precision resistors, so that's pretty darn good. That's well within spec. Now I have the other one. I've measured it previously. It's set up as let's see, here we go, 10.030 ohms, and I'm just going to put them both in parallel here, and you'll see what happens. Now you'll notice as I'm moving this around, it changes a bit. And I'm even going to put my fingers on the resistor just to give it some heat. And you'll see the resistance slightly change because of thermal effects. That's how sensitive we can get with a setup like this. Let me go ahead and put this in here. I'll show you what I'm going to do. Apologies, I'm just filming this quickly on my phone because I hate editing video. So let's put both these together. Now, you'll note they're not exactly the same. There is some variation. Okay. There, and that on there. Okay, so that's how we got them set up. You see we're measuring them now 10.030, and I'll show you some of the math here. So if you see, this is our math equation. So we take the reciprocal of both atom, that gives us the reciprocal of the resistance, or conductance. So the combined resistance should be 5.011 because there's a slight variation here. Now, again, my setup, I don't have the perfect probes. There's a little bit of temperature variation here. But you'll see we're 5.008, which, if I put my fingers on it, we'll warm it up a bit, and you know, we'll get kind of close there. So we're proving here there is some variation, but we're within a couple tenths, hundredths, thousandths of an ohm of where we need to be, of where our math shows us we should be. Again, this is the real world components. When you put two of them together, don't exactly add up to one. You know, 2 plus 2 in the lab is 4. 2 plus 2 in real life, sometimes you have different variations of 2. So the other thing I've done here, and I'll show this, the lab is a mess. I have a box of cat5. It's just an arbitrary box, and of course I got it stripped there. And I've also gone through, and this is kind of a pain in the ass to find the end of this inside the box and not mess up the entire box. So I got these stripped out, and I'm going to show you just what the resistance is of one of them. I've already done some of the measurements here because you don't need to watch me do measurements. I'll show you how that works. So let's just take the white orange, which is a good one. Get this guy out of here. Resistor over there. And where's my patented hold down device? The wrench. Okay. So let's find our white orange pair. Here it is. Put that on there. Put that on there. We are going to see a little bit more variance here because this is a pretty long piece of wire that's in here. I think there's almost 1,000 feet of it. Let's see, is that white orange? Yeah, that's white orange. Or orange white, whatever you want to call it. I normally go white orange because that's just how I was brought up. Okay, so we're hooked up to that. And I measured this before. It was 49.950. And it does bounce around a bit. Oop. Let me see, there's a little bit of variation just because of temperature, things like that. And it's nominally 49.95, which works out really nicely. And if I'm going to go over and measure, let's do the orange wire right now. And these are the same length because they're in the same cable, so they should be identical, right? And yeah, I'll give you they should be identical, but they're not because of manufacturing variance in the real world. They're pretty damn good though. But there's certainly a lot more variation here than in our precision resistor. So I measured this at 50.130 before. That's kind of where it bounces around to. Again, don't have the right clamps here. I probably get a little bit better performance with those. There's a few other things that'll go on with this cable, but we're just looking at the DC right now. AC, you start looking at, well, now the cable acts like an inductor, but it actually acts like a capacitor. Well, when you have those distributed across a cable, it acts like a transmission line, and we get into whole RF theory, and I don't want to go there. So, you know, typically if we add both these together, what we should see is 1 over 49.950 plus 1 over 50.130 gives us should be about 25.0199, rounding to significant digits, should be about 25.020. And let's just go ahead and put these together. I'll show you down here. Okay, got those twisted. Got that on there. I need to find my proper probes. Okay. So now we have white, orange, and orange both in parallel, which you say, well, they're 50 ohms, they should be 25. And I think I just messed something up here. White, orange, orange. Looks good. Okay, so we said this should be 25. There we go. Should be about 25.20, which is right kind of where we're at. There's a little bit of variation here. This isn't a perfect meter either, but 25.20 bounces around a little bit, which is exactly where, looking here. I apologize for having to go back and forth like this. I just didn't feel like editing video. So here's our math. White, orange plus orange. That plus that equals the reciprocal, which is, or the conductance really, that's because reciprocal or resistance is conductance measured in mhos or Siemens. Siemens. Oh fuck. I got a bug floating around here out in the lab. Welcome to Florida. That is 25.020. Now we can do the same thing, and I did some measurements here where we should be. We should be, 12.449. If we put them, put those together. If we put them all together, we should be shooting, just on math, 6.229. I'm going to show you that. Well, I hope it works. Let me put them all together here. Okay. Okay, so we have them all wired up now, and like I said, we should be 6.229 with all this stuff put together, right? Oh, hell, that's great. That's exactly where we should be. Give or take a few thousandths of an ohm. We're bouncing around that area. And again, I got the AC blowing in here. This is not a lab setup for doing this. If this was a laboratory environment and I was doing, meteorological testing, we'd have a much better temperature control. I'd have much better equipment. I'd have just some very specialized stuff. But this is an order of, several orders of magnitude better than a fluke, and we can do this sort of testing with it. I can even see over, a very small piece of wire differences in resistance. Now, you're going to ask, okay, well, this is all the same. What's the actual point of this? Well, one of the questions was, what do we do when we got to carry more amperage? Can we just, put them together like this? And, for the most part, you probably can. The issue is when you get into longer lengths of wire, and especially in house type wiring, you start seeing, okay, well, there's a little bit of variation in resistance here. Well, that little bit of variation in resistance means, according, equals I times R. So as you're, if you're doing lower voltage stuff, your resistance becomes more important. And this level of resistance means that you're going to have some of these wires are going to carry different proportions of current. So it's not going to be, you know, I have 8 amps of current, each cable is going to carry 1 amp in a, you know, an 8-pair conductor. No, what you're going to see is, you know, they're going to carry it proportionally based on their resistance. And there's a whole nother equation you can get into that'll tell you that. And then you can look and say, okay, well, if I'm carrying an amp and I'm dissipating this much, am I safe? Am I not? And in general, that's why this is not permitted in house wiring, to just take 2 wires and, you know, bond them together. You got to use the proper size wire. For low voltage application, you know, you can probably get away with it. None of this stuff is going to cause any sort of a fire hazard or anything like that, with the exception of several of the maybe 100-watt PoE kind of things. But there's enough protection in that kind of stuff, and it's also designed to independently monitor current when you start getting into that. Where you see this sort of stuff where you're bonding, again, multiple cables like this, is in the non-standard PoE. A lot of the micro tick or ubiquity type stuff where it's a 24 volt PoE instead of a standard 48, and it's just blindly putting the power on the conductors without actually having any monitoring or anything like that. That is baked into the PoE standard. The PoE standard carries, you know, a lot of, you know, and one of the reasons it's so expensive compared to maybe cheap PoE or non-standard PoE where you're just putting voltage on the line, is there's a lot more sensing. There's a lot more stuff you have to comply with. So that's the point of all this, that indeed you can parallel conductors. They will, in general, carry, you know, current equally across them, but you don't want to do it over a great distance, and you certainly don't want to do it because, as you can see, there's your resistance of all your different conductors, and they're close to 50 ohms, but they're not exactly. And I'm actually surprised they were that close to 50 ohms, because that's almost 1,000 feet of cable in here. So, but manufacturing tolerances and so forth being what it is, that's why. Anyways, I hope this was helpful, and maybe it was, maybe it wasn't, but it does show you why you can't just take an ohm meter and put it across there, you know, when it's not a 4-wire device. So, and I'm very happy that my math worked out, because it would have been a very funny video if I got to the end here and my equations didn't work. So anyways, everybody have a good one. This is Brian Fields, amateur radio call sign W9CR.